Okay. So, as we said, the microscopic anatomy was more or less clear, I do believe. And just to make it more clear, let's see the um, layers of the heart, how it looks like to understand. And as a result, you can see here, particularly the sections of the heart wall, muscular wall, and not only muscular, to be honest, still. Yeah. So, what is important thing to remember here? This is the part of the section through the wall of the heart. Yes. So a very thin layer. This is interior structure. This is the outer structure, external one. So internally, you can see that this is a very thin whitish layer, and this is our endocardium. Why endocardium? This is literally the epithelial tissue. As you can see here, the special type of epithelium, which we call endothelium. Okay, so epithelium or endothelium here, which is covering the internal surfaces of the heart. Then we have the biggest portion, which is the part of the muscle itself. Yes, so here we do have a cardiac muscle, and that's what we call the myocardium. The next layer, outermost, this is the part of the pericardium. Do you see? This one is the pericardial layer. So the pericardium is the connective tissue layer. But what is interesting here is one thing. Pericardium has the continuation. Let me find this picture to make you to understand what does it mean. Because there are two layers of the pericardium, and I want you to understand how they are covered. Here. That's a good thing. Look. Do you see? This is the part of the pericardium. That's what I showed you right now, which is the connective tissue layer. Although it is composed of two layers. Do you see? The part of the visceral pericardium. Viscera means internal region, internal organs. Yes. So the one which is very closely attached to the organ itself, and the outer part, which is the parietal pericardium, as you can see. Do you see? So as a result, between the visceral pericardium and the parietal one, here we do have the space, which is the pericardial cavity. Most commonly, it's a potential space. It's not that large, but there is some small amount of fluid. You know why? Because when we do have contraction, relaxation, yes, this friction of the heart in the surroundings, to make it to reduce this friction, okay, and the damage to the heart. That's why we do have these particular linings. Like, this is a nice designation of what is happening. Imagine the balloon, okay, which is like, halfly inflated, and as a result, you can imagine that there is the heart which is residing in it. Yes, because two layers of this balloon, as a result, are having more smooth movement on each other, and as a result, this contraction relaxation is giving us a smoother type of a movement. Or here is also very nice picture. So here is already the chamber. Here is the part of endocardium, myocardium, the part of the pericardium, the visceral one, also known as epicardium, as you can see here. And then at the region where the part of the blood vessels are originating from the heart and entering towards the heart, that's where we do have, you see, like the continuation simply. Yes, so it's not just one layer and the second layer. No, they are literally continuous. It's the one structure which is continuous. Okay, so that's important thing what I wanted you to remember. An interesting thing, by the way, I forgot to say that this space, as you can see, this pericardial space, which is mainly potential type of the space, sometimes can be very dangerous. And why? Because in case of, for example, any types of the car accidents or any other type of accidents where we do have the leakage of the blood, in this case, what is happening? We have the blood accumulation between the visceral part of the pericardium and the parietal part of it. And as a result, imagine that the blood, here it is, look, that's what we call the cardiac tamponade. You see, the blood is mainly surrounding like this, the structure of the heart. And what is the problem? It's a very emergency and urgent type of a situation where directly we need to do the surgery. But what is in like why it is the problem? Because as this fluid, most commonly it will be blood, sometimes it can be also because of the inflammation of the pericardium, so because of pericarditis, there are different causes of it, we can have the accumulation of the inflammatory fluid. Okay, in all of the cases the problem is this fluid is literally pressing on the ventricular structures, and the ventricles cannot normally contract and relax, and as a result the main activity of the heart, which is clear, I do believe, yes, it's a pumping. It is not normally performed, so it's not physiologically performed. As a result, we are not having the enough amount of the blood towards the pulmonary circulation as well as towards the systemic circulation, you see? So as a result, the patient can even die, simply to say. That's that's why I told you that it's the urgent type of the situation. So it's an emergency, and most commonly we are using here the surgery. So now, although to understand it better, what I want you to understand also is that if we are talking about the trauma, yes, from the any accident and so on, and there is the simply bleeding, as bigger and more abrupt is the bleeding, sure, it is more emergent type of a situation, yes, because the fluid is accumulating very fast, and as a result we have a small amount of time to evacuate the fluid. In a case of the inflammatory type of the diseases, okay, it can be, sure, it's also acute, but the accumulation of the fluid is not that fast, That's why sometimes we are even doing the thoracocentesis. I remember correctly, it's written like that. I don't remember the word itself, but okay, yeah. Oh, sorry. Yeah, so here is the thoracocentesis. So what we are doing particularly is that through the part of the thorax, we are entering with a large needle, okay, towards, most commonly we are using it for the portion of the thorax itself, but also we are using it to enter towards the pericardial cavity and also drain this fluid out, But again and again, this is mainly will happen in the case of the inflammatory type of diseases, so where the accumulation of the fluid is not that fast as in the case of a traumatic type of the injury. So here comes some physiology now of the heart, which is associated with important function, a cardiac cycle. So what is the cardiac cycle and what is dependent on? So coming back to the heart again, what we need to remember. Before understanding the cardiac cycle, I want you to understand how our cells are functioning, okay? And here, the most important thing is about the making our cell, to shift from the resting conditions to the active, excited condition, okay? And this can be happening only with one thing, with the help of the different types of the ion change. Because you know that normally when we're talking about the resting conditions of our cells, this means that mainly nothing is happening inside. In this case, we do have particular charge across the plasma membrane of the cell, And this particular charge is most commonly a negative charge. In a different cells, we have a different types of a charge, to be honest. And plus, I will also open if you remember, I showed you Irafox once, yeah? Just a second. as well as, if I remember correctly, I have also a nice presentation for that, but whatever. So main idea for me is right now to show you this thing. Just a second, please. I don't, the 7th chapter. Yes, I do believe. Yeah, good. So the 7th chapter, that's what we need particularly. And let me explain this part for you. What do I mean? Mm-hmm. Although here is a good example of the same resting potential and action potential in the case of the nervous tissue, but the same happens in the case of the muscles too, you know? So what is the most important part here? Let me show you just to make you to understand what I mean. Yes, here it is. Look, in the part of the plasma membrane, so this is the axon with the plasma membrane, okay? So you see, normally in the resting condition, the potential, so the charge of the interior of the cell is always minus. For example, in this case, it's approximately minus 70 millivolts. That's what you can see particularly here, minus 70 millivolts. And this means that most commonly there is no particular action inside of a cell. Okay? The same happens for the cardiac cell. If there is a low potential, sorry, a low voltage, so approximately up to like 65 to 70 minus 70 millivolts, so it is the negativity inside. So the nothing is happening, no contraction, nothing, so literally it is relaxed. Okay, so how we can change the negativity, electronegativity inside of the cell? The only thing what we can do particularly here, this is the exchange of the ions. You know that the ions are the atoms which are either lost or gained the electron. Yes? Did you understand what I said or not? Till now, is it clear? I do believe you are studying, yes, biochemistry portion. Guys, yeah, good. So when we're talking about the ions, we can have either positively charged ions, or which are cations, or we can have the negatively charged ions or anions. Yes. So as more amount of cations will be entering towards the interior of the cell, electronegativity will be decreasing. So from minus 70, it will go up towards the 0 and even towards the plus. Am I right? So these particular changes in the electronegativity, this is the one towards the positivity. This is the one which is helping us to do important thing, which is helping us to activate the cell. In the case of a cardiac cell, it means that it will make it to contract. Okay? So as a result, what you see here particularly is that if we do have the minuses and the very low electronegativity, then we do have the, very high electronegativity, so low charge. As a result, we do have the resting potential of the membrane, okay? But as soon as we do have, you see, influx or entrance, and that's what you can see particularly here. Look, influx of the sodium, again, influx of the sodium, and next parts of the cells are undergoing the change of the electronegativity towards the positivity. And what is happening? And this is particularly in the case of a cardiac cell, will help us to make it contract. So as a result, we have the action potential. That's how we call it. Normally we do have nice. Just a second, let me find it for you. Okay, this portion is not interesting for me. I just want to show you how it looks like the action potential itself, right here or even here. Just a second. Resting potential vs action potential. Look, yeah, here it is. Look, a good example of the action potential. So as we do have, nothing is happening in our cell because it is electronegative inside. But as soon as we had the stimuli, we have the opening of the channels for the cations, so positively charged ions, and they're starting to enter. So we have an influx of them. And as a result, we have the electronegativity, which is changing. So it becomes more closer to the zero, so more electropositive. And as it comes approximately to minus 55, you see in the fraction of the second, we have the change of the whole plasma membrane potential from the resting one towards the positive one, you see? So towards the action. And that's what we call the depolarization. You see, here is the voltage in the millivolts. So from minus 70 towards the plus 40, as you can see here. That is particularly what gives us the trigger for the cardiac cell to contract, you know? Sure, action potential is not something like a perpetuum mobile, meaning that it's not continuous. Yes, sure. As soon as there is entrance of the cations, then there is a like the other cations are leaving the cell. And why? Because we need the next action potential also. Yes, in particular period of time. So we need to make the whole membrane potential back again to the normal one. I mean, to the resting one. That's why we have the period of the repolarization, as you can see. So it goes down towards the minus, and as a result, we do have a portion of the even refractory period. Why? Because there is a very low voltage, and as a result, there is nothing even can help us directly to give the depolarization. It needs the time to go back to the resting state, and only after that we can have some formation of the new action potential. So the same idea happens in the case of the heart, you know. So because the heart, I mean the heart cell needs to be activated, something should trigger it. Okay? But the most interesting thing that the heart doesn't need any other cell, for example, the neuron, to trigger this action potential. It can do it itself. That's why I told you, if you remember, in here was written this that where it was this portion. Just a second. And where it was these words were very much important for me. That's why I will just show you it back again. That the cardiac cells, or maybe it was here in the microscopic anatomy. Yes. Cardiac muscle has the ability to continue to contract and relax rhythmically, even when it is separated from its nerve supply, and is therefore not being acted upon by electrical impulses from the nerve tissue. You see, this one sentence explains the idea that the part of the cells of the heart are modified, that they can themselves open the channels, okay, for the cations to be entering towards the cell, to change the electronegativity towards the positivity, and as a result to give the contraction to all of the cells. You see, because you remember that I told you it contains these gap junctions between the cells, as it was in the case of smooth muscle. Yes. And as a result, with the help, if one cell got this large amount of cations, it will be passing through these gap junctions to other cells, and as a result, we will have the contraction of the part of the heart. For example, the atrium, or the part of the ventricle. Till now, was this clear or not? Just a second, please. Okay, guys, I'm sorry, I'm back. So, as a result, look, so change, okay, in the potential gives us the activity. An important thing that this modified type of a cardiac cells are the ones which are starting this change in the potential and as a result starting the activity. So, coming to the portion of the cardiac cycle, you can see that everything begins in the specialized group of the muscle cells, okay? And that's what we particularly call the pacemaker or sinoatrial node. Normally, we don't have here a nice picture, but let me show you here, okay? We call it conductive system of the heart, okay? Or conductive conduction system, whatever, the same thing. So do you see um, this one, for example? This is a nice picture. You see, we have the aggregation of the cells, which are having the ability themselves to open the channels for the cations and make them enter inside of a cell, okay, and change the electronegativity. So here, so starting from the sinoatrial node, this is the first thing. So here, as soon as we do have the formation of the action potential, this action potential is propagated. So it's the right atrium, by the way, yes, on the lateral wall of the right atrium and more posteriorly, very close to the vena cava. So you can see that we do have this sinoatrial node or pacemaker. This is the first place where the pace is produced, okay? Now, you see that this action potential is propagated through both of the atria simultaneously. It's like needing the fraction of the second to be propagated, okay? And as soon as it comes to the next aggregation of this type of the cells, this is the AV node or atrioventricular node because it's literally localized in the junction of the atrius and the ventricles, okay? So particularly here, we do have a large amount of the connective tissue, and this connective tissue is the one which is holding the valves, leaflets of the valves, you know? And because the connective tissue is very difficult to make the change in the electrical potential, you know, it needs the time to go through this region, and during that particular time the atria are contracting, you see. So again, we had the formation of action potential in the pacemaker in the sinoatrial node. It went to both of the atria, and as it came towards the atrioventricular node, it made like a delay, a pause, because of the tissue difference there, okay? But that's important pause first. It's physiological. It's good because that gives a time for the atria to contract and start the relaxation. Because at that time, the blood will enter towards the ventricles. And at this time already, the impulse will pass. This pause will go through. It will be, the delay will finish. And as a result, the action potential will go through the other part of the conductive system. And this is, you see, atrioventricular node. This is the AV bundle or atrioventricular bundle, or also known as bundle of His, H-I-S. And then the bundle is subdivided into two parts, one right, one left. So one entering towards the right ventricle, one entering towards the left ventricle. That's why we said left bundle branch and right bundle branch, okay? So all LBB and RB. So LBB and RBB, okay? So as a result, as soon as we have this delay, it already finished and it passes through all of the parts. Here you can see the very, very strong contraction of the ventricles. When the atria are already having rest, they are relaxing, and the blood now from the ventricle is going towards the large arteries. You see? So that's the whole idea of the cardiac cycle. Okay, and again, coming back to the resting position, when we do have a portion of the atria, and when we do have, like, they are relaxing, then there is the relaxation of the ventricles, and again we have the pacemaker, which starts to produce the mm, action potential. It passes through both of the atria. We have the contraction. It is delayed through the atrioventricular nodal region, and then goes through the ventricles, and then the ventricles contract. So as a result, we have atrias, ventricles, atrias, ventricles. That's how particularly they are contracting, rather than all of them together. Is this part clear what I'm saying? Do you have any questions in this case? Hmm? Guys?
So basically, do you just want us to explain how the heart just goes from rest state to excited state? We don't need to know like
Sorry?
all of the.
Could you say it again? I didn't understand. What you should know?
No, I'm just saying. Do you just want us to explain how the resting potential occurs and how it goes from a rest to an excited state, and that's it?
Sure, you need to understand that we are talking about the movement of the cations through the plasma membrane. So, and that the plasma membrane permeability is changing. Yes, I want you to know that. I want you to understand that. I don't want
Okay.
you just to say that okay, there is a pacemaker which is producing the pace and so on. No, you need to understand the physiological background of that particular pace formation. Yes, so that's why I connected this part to the action potential and the resting potential. Okay, sure, I don't need very much details in the part of action and the resting potential. Resting and action potential. But what I want you to understand that any type of a change in the cell environment, this is because of the change of the permeability of a plasma membrane. Yes. So if the plasma membrane lets something, some ions, some molecules, and so on to enter towards the cell, or vice versa to go out, sure, the interior is changing, and as a result, the function is changing. So, and if we talk about the ionic type of the concentrations, yes? So mainly here, when we talk about the cations, and most commonly it is the sodium ion, because it is plus, positively charged ion. And as a result, I want you to remember that this is the one which gives us most commonly the action potential. This one I want you to understand, because I just don't want you to learn by heart something that there is some pacemaker and something is happening, okay? I just want you to understand it very well that there is the permeability of the membrane which is changing. Most commonly, the permeability of the membrane changes because of the nervous tissue regulation, okay? But when we say about the heart, that's why this one sentence was important. It can be contracting and relaxing rhythmically. What does it mean? It means that it can itself start the change in the permeability of its own membrane, and as a result give us the action potential. And mainly that's what is happening, because even if you will, for example, cut the nerve fibers, for example, of the parasympathetic innervation, which is slowing down the heart rate, you will see that nothing will happen. I mean, it will be contracting and contracting itself. Just one thing, what will happen is that because it can be accelerated, the heart can be accelerated, and without this control, it just can be you will have the high heart beating, and that's all. But it can do it itself, and it does it itself. That's what I want you to know. So as a result, you can see here particularly that the full cycle occurs as follows. Once stimulated at the pacemaker, waves of electrical activity spread quickly to the both atria and so on. So you see the whole explanation. And one important thing here, just for you to know this terminology, that when the LBB and RBB are starting to enter towards the walls of the ventricle, it is giving us even more branches, and that's what we particularly call the Purkinje fibers, okay, which are also modified type of cells, as well as the sinoatrial node or AV node or the bundles and so on. And here we do have a fast propagation of the electrical activity. So here you would say one important thing, that okay, if the pacemaker is the one which can change the permeability of the membrane and as a result produce the action potential and so on, why the others cannot? They can. Do you know AV node can do that? Bundles can do that. Purkinjes can do that. That's why, by the way, the different types of the arrhythmias, so not normal rhythm of the heart, are dependent on the problems with the pacemaker, and as a result, we sometimes can have some formations of these paces in the different parts of the heart. But that's a problem. Why? Because it will not be propagated to a long distances, and as a result, we will not have a normal contraction, simultaneous contraction, so less force, which is pushing the blood towards the arteries, and as a result, we'll have the problem with the blood supply of the organs. That's why I do believe you have heard about the artificial pacemaker, which we are using, and we are using it in case of a treatment. So when we are performing the surgery and simply putting the artificial pacemaker, which is producing the pace itself, and as a result, we do have a normal heart rhythm when we do have the contraction of the atrius first and then the ventricles. Okay, to be honest, the contraction of the atrius is not the big problem, because I do believe you have heard about the atrial fibrillation, yes, and ventricular fibrillation. Even on the ECG, which we are using, or EKG, so electrocardiography, this is the way how we can. So this is the way of the recording the electrical activity of the heart from the different perspectives, So this is the one of the classical representation of the EKG or ECG, where you see the P wave, where you see the QRS complex and the T wave. You know what is this? P wave is the depolarization of the atrius, and as a result, after that, we have a contraction of the atria. Then you see we have this delay a little bit, and then we have the depolarization of the ventricles. Do you see? QRS complex. And then we do have the repolarization of the ventricles here. So in the case of the atrius, why it's not seen the repolarization? It repolarizes, but at the same time when we have the depolarization of the ventricles, meaning that while in the atrius we have the change of the action of the potential in the cell, in the atrius, which becomes more electropositive, that's what we can see by the P wave. Okay, the the change of the action of the potential in the ventricular cells, okay, that's what we call the depolarization there too. That's what is seen by the QRS complex. But at the same time, when we have the depolarization in ventricles, it is so strong because the ventricles are larger than the atrius. That's why the wave of the atrial repolarization is not seen. Okay, when it goes again to the resting conditions, is not seen. In the case of the ventricles, it is seen. You see, and we do have this repolarization. So when we have back again to the normal conditions, I mean the resting conditions. So as a result, we have this type of the complexes approximately 60 per minute. So this is the heartbeat, yes? So 60 times per minute. So a normal heartbeat is approximately 60 to 100, where less than 60 is the bradycardia, or very, very slow type of the heartbeat, and vice versa. Higher than 100 is the tachycardia, so a very fast type of the heartbeat. In the case of the adult humans, please remember that we do have the normal type of the heart rate is between the 60 to 100. Over it is okay in case of the exercise. Okay, when we do have the exercise. In case of the bradycardia, we can find the bradycardia, for example, in the athletes, because their heart is working a little bit in another way, because we do have the increase in the muscle because of the over-exercising and so on. Most commonly, we can see the part of the bradycardia or slow rhythm. So continuing, you can see here this nice picture showing you again pacemaker, which is the sinoatrial node, atrioventricular node. They show you the propagation of the whole electrical activity. They show you then that we do have the contraction. At the same time, they say that we have here the delay, and then we have only the propagation of this electrical activity towards the ventricular system, and as a result, we have the contraction of the ventricles. You see, that's the whole idea of the cardiac cycle, and that's how it looks like. And that's here they tell you that when we have the this contractile activity, so when we have the contractions of the atria and the blood is entering towards the ventricle, then the ventricles start to contract, and we have the closure of the atrioventricular valves. And then the blood is entering towards the large blood vessels, and again we have the closure now of the semilunar valves. So what is happening? That's where we can hear this lub dub. Yes, so lob, as you can see here, when we have the tricuspid and the mitral valves, so atrioventricular valves closing together. Dub is when the aortic and the pulmonary valves are simultaneously closing. Till now, is it clear everything? I think that today we will not finish the cardiology, but it's okay. I will use the second lecture also. So, did you understand till this part, this information? Good. Let's go through some functions of a blood vessels, and that's where we'll finish for today. And the next lecture, I will go through all of this information till the end of the cardiology. As a result, in the case of your midterm, you will have, please write it down. In the case of your midterm, you will have the portion of the out of here, I mean from this guide, you will have the, just a second, where are the chapters? Yeah, here it is. So chapter 1, okay, and a chapter 2, that's for sure. From the Ira Fox, if you remember, I talked about these things here. I'm sorry. It was the first chapter, if I remember correctly, yes? Yeah. Here we do have this introductory part where we have these feedbacks. So chapter 1.1 in the Ira Fox. Chapter 1.1, then 1.2, this homeostasis and feedback control. Yes, this everything. Till 1.3. I don't need 1.3, okay? Because these tissues and everything we have, I do believe, here. Yes, I need the whole first chapter. That's for sure what I need. Also, we have some presentations of mine. Just a second. Let me check, okay? It's just not to forget. So here we do have this part of the introduction. You remember? So this part I also need, as well as in the part of the Moore's clinically oriented anatomy, we have covered anatomical medical terminology. Do you remember? I also need it. That's for sure. That's what will be in your midterm. So this is in the Moore's clinically oriented anatomy, is literally localized in the parts of the, do you see? Here is introduction to clinically oriented anatomy. It doesn't have the chapter, I mean the number of the chapter, starts from the page 2. So approach, systemic anatomy, anatomical medical terminology, this everything. Movements. So till page 12, I need everything. Okay? Is it clear? Is it clear for everyone? I do believe yes, yeah? Good. Okay, so that's what will be in your midterm. So on the next lecture, I will finish with a part of a cardiology, And as a result, you can already be prepared for your midterm. Okay, one thing what I want to talk now about was particularly the portion of the functions of the blood vessels, and that's where particularly I will finish for today. It's not a big thing, but still I want to make some understanding. Okay. So as we said, we have two main types of a blood vessel. Oh, sorry, three main types of the blood vessels. These are arteries, these are veins, and these are the capillaries. And according to the arteries, which are more branching into the smaller arteries, because according to the diameter, there are different types of the arteries there. And the smallest one are the arterioles. So, and their main function is the transport of the blood full with the oxygen, full with the nutrients towards the tissues from the heart. That's important to remember. And here comes the idea of exception or the paradox. As I told you, the pulmonary artery, which is leaving the heart, but the right side of the heart, contains the deoxygenated type of blood. Am I right? Yes, because it enters to the pulmonary circulation to exchange the carbon dioxide on the oxygen. Veins are the blood vessels which are by their definition transporting the blood towards the heart and mainly contain the full of the waste products and the carbon dioxide type of the blood. But again, here comes the paradox. Why paradox? Because we have the pulmonary veins, which are the ones which are entering towards the left atrium from the lungs and contain the blood which is highly oxygenated. Yes? Now, what is interesting is that in the case of capillaries, the ones which are the branches, the smallest branches of the arterioles, important thing here is that what type of the wall do they have? We'll see that in the microscopic anatomy in the next lecture, but important thing that compared to the arteries, even arterioles, as well as the veins and venules, their a wall is extremely thin. Why? Because their main function is literally the exchange of the fluids between the vascular lumen and the tissue. Okay? So, sorry, as the result, at the beginning of the capillary, we have the most of the movement of the fluid away from the capillary towards the tissue. As it goes through, more and more of this more and more of this fluid is coming back again towards the capillary. Is that clear? So for the next week, I will continue with a part of the microscopic anatomy. What are so histology? What are the main tissues presented there? And what are the functions as well as what are the functions according, that's important thing, functions according to the structure of the wall of the blood vessels. Do you have any questions? Mm-hmm. Good. Okay, then for today we can finish. Thank you very much, and we'll meet you next week